real difference here and producing what became the 2018 cloud report. So again, it wasn't intentional, but it was sort of serendipitous along the way. So let's take ourselves back to sort of our understanding at the time that we were doing the cloud report. In 2017, we'd actually done a lot of benchmarking with different clouds, and our analysis at the time was that GCP outperformed AWS. And we had expected that to carry through. We looked at it in great detail. And then what we found is that didn't even last 1 year. And there's a couple of reasons for that we'll talk about in more detail. In our report, we found that there was sort of a 40% difference, but that's sort of less material than the fact that things change. And that because they change, it makes it hard to know. You do an analysis one time, it doesn't mean that it'll hold true for the next time that you actually want to do a comparison here. And that sort of takes me to one of the most important points of the entire presentation here, which is this has to be continuous. It has to be regular. You have to have a regular cadence of these kinds of analysis because things are changing so rapidly. OK, next I'm going to talk about some gotchas we encountered along the way that are interesting challenges that if you were to try to do this yourself, you might need to know about or think about in the process. The first is that you have to pick your instance type with care. And what I mean by that is that you have to know exactly what you're getting yourself into. There are many different options available on all the different clouds that make it a little confusing about what the actual differences are in these instance types. And so we can see one example of that is just in the nomenclature themselves. The AWS machine types, they go from like M4 to M5. They have Ds included in them sometimes and not. And the difference in those things is about versioning, right? So AWS will sort of signals to you that M is a certain type of machine. If it's 4 or 5, it's a version number, so the 5 is newer version than the previous version. And then the D signals if it's SSD or not, or other things in the process. And so there's a lot to keep track of and sort of maintain. And in AWS, the names are so similar. You'll have a M4D.4x large and an M5D.4x large. And it's a little tricky to keep track of these kinds of things. But you always kind of want to be on the newest version because all of the new versions have updates. Google has done something similar. Actually, historically, they stuck with the N1 standard and actually updated things in place. And they told us when we talked to them about it that one of the reasons for this is that they thought it was helpful for developers to not have to change their scripts. If you scripted for an N1 standard, then you were always going to get an N1 standard, and they could just update the hardware behind the scenes. It turns out that they are, at least in some capacities, updating that because we've learned that they have an N2 standard now, or N2 high memory, or N2 series of machines that are the newer machine types with newer processor types. And so we'll actually be testing those as a part of our efforts for the next version of the cloud report. In addition to picking your instance type, so the N1 standard or the M5 standard, you actually have to know about the processor type that underlies this. And this is a little tricky because it's not always front and center in the documentation of what's there and how to think about it. So for example, the N1 standard from GCP has both the Skylake and Broadwell processor types. We found there were to be better performance with the Skylake ones. But unfortunately, you can't just know that something is a Skylake either, because GCP actually got Skylakes first, then AWS got them, and the AWS ones were slightly newer, slightly faster than the GCP ones. So you can start to see what I'm talking about here with the complexity involved of staying on top of this. You have to know the processor type. You have to know how new that processor type is in order to understand what their performance profile is going to look like. In the cloud report we did last time, we tested a bunch of different types. On AWS, we tested the general purpose, the compute optimized. We tested storage optimized. On the GCP, we tested different processor types. We tried to hold things as consistently steady across both as we could. And we tried to look at both persistent disk, SSDs, and different configurations here. This is actually sort of just scratching the tip of the iceberg here. And one of the things that we actually have in the 2020 report is many more machine types tested. For the comparisons, again, this is what I was talking about, was sort of trying to make things as similar as possible. They both had 16 CPUs. They both had the same relative amount of storage. GCP actually offers a little bit more memory on the same comparison than AWS offers. And so it was important to sort of keep those things in mind. as I said, we're not going to really talk too much on specific results throughout this presentation, but these are the kinds of things that you have to account for if you're going to compare across clouds, is that no cloud has exactly the same setup as another cloud. You have to make some tolerances and some estimates in order to try to make things as aligned as possible. The other point that's really important here is that there is actually no one-size-fits-all. There's not one best machine type. And so this is a little nuanced, but for your workload, it might be better to use a memory-optimized one, or it might be better to use a compute-optimized machine. And so that's something that you kind of have to keep in mind as you're thinking about this, is that we will produce data, we'll show you how to produce data, we'll explain these kinds of things, but there's really no substitute for actually taking your workload and trying it out on different machine types. OK, so that's some background, some understanding of kind of how we got here. Let's talk about some of the open source tools we used in the report itself. We use 3 micro benchmarks, in addition to sort of a more macro benchmark in TPCC. The first being CPU. CPU for Cockroach is one of the most important things because we're processing a lot of information. We're flushing things to disk. We're kind of doing these types of compute-intensive operations, and so CPU tends to be really important for us. You'll see this repeated a few times throughout the presentation today, but the most important thing you can do is pick the right tool. And it's kind of the first thing that you have to think about anytime you're looking at this, because they're all subtly different, and they all have different sort of tips and gotchas along the way. For CPU, we like stressng, and we like sysbench. We think that they're both pretty good tools. They're both open source. They both let you test out CPU in terms of exercising floating point operations or different kinds of complex tests of CPU itself. And they're both sort of, they contain sort of the best elements of CPU testing. And they allow you to provide detailed and aggregated results across them. We actually ended up picking stressng because we thought it was a little easier to use, and we liked the stressors it used a little bit more. Stressng is actually kind of funny. It wasn't intended to be a CPU benchmark when it was built. It was actually meant to stress the hardware as much as possible to see if it would result in failure. And what the founders of it found is that it was actually a really good way to test CPU as well. And so it did its own like pivot as a startup or pivot as a test to kind of focus more on CPU moving forward. And so it comes with a few different what they call stressors here, or ways to stress CPU. These are separate tests within the benchmark. There's the matrix, the sim, and the branching. They all test different components. The matrix, for example, tests the floating point operations. The sim stresses the kernel semaphore, and so on. And so we like them because you could see different ways of simulating different activities on the benchmark itself. The final thing I'll note here is that stressng measures things in an operation called BOGOS operations, or BOGO ops per second. And they sort of chose that name with care, which is that these are sort of arbitrary measures. You can't say that because you can process a certain amount of CPU in BOGOS ops, that you can also then translate that to your workload of a certain number of transactions or a certain number of queries or things along those lines. It also sort of helps you to have this intuition that you're measuring something important here, but not to lose sight of the direction that you need to go overall. So behind me, you'll see example data here from the report. And as we go through these charts, it's not really about the outcome, but more about what you would be looking for as you were sort of conducting an analysis, or what we look for as we conduct an analysis like this. So for all these charts, you'll see AWS in gold. You'll see GCP in blue. And then there'll be different kind of measures throughout. So this is a CPU throughput chart. Along the x-axis, there are all the different runs that are in place here. So we ran this multiple times. And then the bogus operations for the throughput here is then what's on the y-axis. And so what you'll see here is you'll see two things. One, AWS in this example actually outperformed GCP. Again, that's a point in time. A measurement at a point in time doesn't mean that's true today. But the other thing you'll see is that both GCP and AWS are very consistent. And that's also something that really matters when you look at these types of charts, is that you want to have predictable performance. You want to know that you're getting the same thing each time you come back to one of these machine types and tests. And so that's something that we'll kind of talk about throughout, is this predictability in addition to the raw results itself. There's a few tips and gotchas on the CPU side. First, we like the CPU and matrix stressors the best. We think that they're the most representative of real workloads, of actually making the CPU be compute intensive. They test the square roots, the fast Fourier transformations. Matrix has a lot of mix of memory caching and other sort of mixtures of tests out here. And so it's, your mileage may vary. We certainly think that you could test with multiple stressors, but we found these to be sort of the most representative of what mattered here. The next thing is returning to this notion of bogus operations or BOGO apps, is you can't actually compare them across stressors. So they're stressor specific. And that's really important because you might see a high return on a matrix test and a more modest return on the CPU test. And you can't really compare those operations. You can only compare within the individual stressor itself. OK, next up, let's talk about the second benchmark we talked about here, network. Network is obviously super important. I think one of the things that sort of goes without saying here is that network is something that you have to really be careful to hold constant when you're testing across different clouds. You have to make sure that your exact setup is the same. You want to be a good scientist. You want to make sure that you're measuring what you think you're actually measuring here in the process. We typically talk about network in two main ways. We talk about it in throughput, and we talk about it in latency. Throughput is kind of intuitive. It's what you'd expect. It's the sort of quantity of data being sent or as a packet across the network. Latency is how much time did it take. Sometimes we also talk about round-trip latency of returning back on top of that. And these are always sort of the things that we're going to be thinking about here is this throughput and latency information. So like we did with CPU, one of the first things we did was evaluate what are the tools that are available out publicly, what are the open source ones. I didn't mention this earlier, but one of the reasons we really like open source tools is because we think that a benchmark isn't a benchmark if other people can't reproduce it. And so we want to make sure that those reproduction steps are always available so that you don't have to take our word for it. You can actually go verify that we've produced the same thing, And we're not perfect either. We make mistakes, and so if we have reproduction steps available, other people can vet our work. And it's just like any kind of good coding in general is this having this peer review is available. And so that's why we chose open source. We wanted everybody to have access to these tools as they were trying to replicate our findings or look at them themselves. Ping is a pretty widely used tool. It's really simple. It only measures really latency here, whereas netperf, or sometimes talked about as iperf, can do both, latency and throughput. We actually ended up choosing ping for our latency test and netperf for our throughput test. And so we'll talk about, again, sort of examples of results here. Like the charts that we talked about earlier, GCP is in blue, AWS is in gold. We are testing here the network throughput. But this is a histogram now. And so what that means is that we have sort of different buckets along the bottom, and then we're counting how many times those runs fell into those consistent buckets. And this is important because now we're looking at two things. We're looking at, one, where are the results falling? And so in this example, again, this was AWS slightly outperforming GCP. But what we like about AWS is very straight and narrow. All the results are sort of on top of each other. You can get the same results every time you run the test. Whereas GCP's is more like a curve. It's a little spread out, right? And we like things to be more narrow because, again, it's more predictable. One time you have a run on fall on the bottom side of the curve, the next time you fall on the top side of the curve, that's unpredictable performance for your customers. Similarly, when we start to talk about latency, we want to measure it in the same way. We have it on the same scale here in terms of a histogram. But now, instead of wanting to be as high as possible, because throughput we want to be as far over as possible, we want to be as low as possible. We want to take the least amount of time possible here. And so again, at first blush, it looks like GCP is a little bit more narrow. The chart is not quite as spread out. But if you actually look on the side here, there's a couple findings that are much further out here. And so that's an example of something that you want to take into account as outliers. How far does the spread happen? Even if most of the time it's pretty predictable, if there's a few outliers here, that can cause big problems overall. Now, we learned a couple things in this process. And this is actually one of the few ways in which the test will be different next year, is that actually our friends at GCP told us about how ping with its default setting can actually measure C states a little bit incorrectly. It catches the CPU coming in and out of them in the process. And so you can actually pass an interval flag to that makes it happen more frequently. And this makes it a little bit more fair because then you're actually measuring what you think you're measuring here in the process. And so that's a good example of being able to collaborate with them after we release the results and understand an opportunity for us to improve what we do for next time. There's a couple other ones that are fairly obvious, but just are worth repeating, which is the remain conscious of your network topology. It's, it can be confusing, it can be a difficult topic, but you just want to keep things as apples to apples as you can. Also, all of the clouds provide internal IP addresses, and if you're not using the internal IP addresses, you're introducing other barriers into the network measurement here, so you got to stick on top of those. And then probably the final thing is just being consistent in your network protocol and understanding which network protocol is the appropriate one to use in a particular setting. The last benchmark I'm going to talk about today, micro benchmark, is storage and I/O. At Cockroach, we care a lot about storage and I/O because we're processing these things, we're flushing to disk, we're keeping on top of these things actively. We also have our familiar friends of throughput and latency here. And these are sort of measured in the same way. They're amount that you can process through, amount of latency that times take. But the distinction here is that now we are talking about both writes and reads. And write is exactly what you'd think it would be. It's the performance of write operations. This is writing information to disk, right? Reads is exactly what you'd think it would be. It's reading information from disk. How do we know what's coming back up off it? So, like we've repeated every portion of the slide, the tools make the benchmark. And for this, we actually found that sysbench was the right option. And so sysbench is kind of interesting because it got its life originally as a sort of database benchmarking tool, and it sort of expanded out to be used in many capacities here. It's open source, it's multi-threaded, you can use Lua scripts with it, it's quite easy to use, and it can be run on file-level system workloads. And so it provides us an opportunity to test storage in a way that was meaningful to us, and we thought it was the right tool for the job here. Again, similar chart to what we talked about before. This is now back to number of runs. It's talking about threads along the bottom here. And so, GCP in blue, AWS in gold. Originally, if you look at the low thread count of like 1 thread or 4 threads or even 8 threads, AWS looks like it's actually outperforming GCP. But as you start to get into more concurrent threads, a greater number here, GCP starts to catch up and then actually overtakes AWS's performance here. And so, again, this is the kind of thing where you have to be thinking about the number of threads. You have to look at it in multiple capacities, or you might miss part of the really important story here. Latency is also really interesting here. And so on these charts, the solid bar is the average latency, and the dotted lines are the P95. And there's the story of AWS kind of being a lower latency here because it's lower in the curve in the process. Excuse me. But what's also really important is how close together those curves are. So again, the closer together, the better here, because what you're saying is that your average user is also getting the same experience as your P95 user, as your 95th percentile out. And so we want to be as close to possible together as we can get here in the process. A couple of tips and gotchas here. If you're looking at storage, there's different ways that people can think about these things between sequential and random access, between reads and writes here. And so there's the sequential write, the sequential read, the random write, the random read. You want to choose the right one for the benchmark or measure that you're taking into account here. We also care a lot about fsyncs here. And so there's multiple different fsync options here that you can consider in the right option here. And so this is something that we care about in terms of the wall durability, and we want to test fsyncs after every write here in the process. And then the last thing is actually, for cloud-based, there's a difference in persistent storage and how those things are taken into account. So on the AWS side, there's actually 2 options. There's the GP2 and the IO1. And so we want to, when you think about those, they're provisioned differently. GP2 comes with a standard amount of I/O, whereas the IO1, you actually have to choose how much to provision. And so if you choose too little on your provisioning, you're not going to get the top performance. If you choose too much, you're going to pay a lot for the performance that you're getting. And so you just have to understand that it's not sufficient to just understand that something is persistent disk or not. You actually have to understand how the mechanics of that works underneath the hood. The final benchmark I'm going to talk about today is TPCC. And so, we've talked about the micro benchmarks and built up to this because these explain the actual underlying differences in the hardware itself. But you have sometimes a hard understanding of thinking about how does that translate from CPU being in bogus operations to what an actual application might actually experience in terms of performance. And so we like TPCC because it's an industry standard benchmark. It's something that's been around for almost 30 years, so it's kind of stood the test of time. And it's also, it's quite complex. It simulates an e-commerce retailer, so there's different warehouses available. There's transactions across warehouses. Things are being read, they're being written. There's lots of activity going on here. And so it's something that's kind of a nice test that we believe is kind of most representative for OLTP workloads. It's just something we care about at Cockroach. And so it's something that we thought would be a good way to sort of roll this up to what an actual application experience would be like. So one of the first things we thought about was perhaps the SSD or persistent storage might be the reason for the difference between the outcomes that we saw in the last report. And what we found is that that's actually not the case. There's both SSDs that performed well, EBSs that performed less well. So we couldn't really quite answer our question yet of why was AWS outperforming GCP in the last run of this report. So the next chart we did is we actually started to investigate what had changed about the actual clouds themselves. AWS had invested in 2018 in this thing called the Nitro System, which is a virtualization layer that actually, all of the machine types that had access to this virtualization layer actually started to perform better than the other ones. And so this is what we're talking about when we're saying things change. This virtualization layer, this Nitro System, didn't exist previously, and it helped to sort of win back some of the performance gains that the GCP had seen. So what did we learn from this exercise? The first thing is that there was conventional wisdom that hardware performance was plateauing. And what we found is that's just not the case. It changes every year. And you could see this because the clouds are making huge investments in it. We've already talked about the N2 standards from GCP that are coming out. There's new machine types from AWS that have come out. And there's still a big race here. And in fact, if you're trying to count sheep one night and you're having trouble sleeping, you can dive deep in the 10Ks for Amazon and for Google, and you can look at the investment expenditure here, and you could see the just zeros and zeros and zeros that are in place for the hardware expenditures that are happening here as the clouds race to have the best possible performance. And so this is something that we expect will continue to change, and they'll continue to sort of challenge each other on. The next point is that benchmarking is really complicated. It's hard to stay on top of. It has to be run on a continuous process. You have to pick your instance and processor type with care. You have to pick your tools with care. You have to understand how those tools work. You might miss things like we did with ping and its periodicity. And so this is the kind of thing where it requires a sort of deep investment of understanding in order to actually stay on top of the differences here. The last thing I'll talk about is that we're here at a multi-cloud conference. We've had various presentations talking about sort of avoiding vendor lock-in or the challenges of being able to switch from cloud to cloud. And there's real benefits from sticking to an individual cloud, right? They'll give you discounts for maintaining the same storage as the same database as the other options. But there's real cost to that as well. And so if you operate a database like Cockroach, you can start out on GCP when it has better performance. Then you can move to AWS if its performance changes. And then you can move back to GCP later on as the performance changes are in place. And so if you accept the benefits of sticking to one single cloud, you won't be able to sort of stay on top of the most cutting edge changes and be able to take advantage of those moving forward. The last thing I'm going to talk about today before I take questions is a teaser for the upcoming cloud report. And so you might be a little confused because I've been talking about the 2018 cloud report, and the slide behind me says the 2020 cloud report. And you might be wondering, do we take a year off? Like, what's going on? Why are the numbers different? And it's because we released 2018 cloud report in November, and then people were still using it and consuming it in 2019, and it sort of has been the most recent thing we put into date. And we're planning to release the upcoming cloud report here fairly soon. And as a result, we realized that we should treat this more like a fashion line, or more like an automobile line, in which we're actually calling it the 2020 cloud report, even though it's coming out at the end of this year, because it's for next year. The biggest announcement we have about the report is that we'll actually be factoring in Microsoft Azure into the report. As I talked about way back at the beginning of this conversation, we didn't set out to create a cloud benchmarking report. We sort of stumbled upon it serendipitously. And so if we had, we would definitely have considered Microsoft Azure in the conversation here. And so what we decided is that if we're going to keep doing this on, we need to have Azure as a part of the cloud space in order to make the fair comparison among all the top 3 clouds. We also realized that it's quite difficult to run all these micro benchmarks. It's time-consuming, it's challenging, and so we will be open sourcing a tool that lets you automatically run through these benchmarks. And this tool kind of goes through each one. It has the steps in place and sort of it sort of takes the need out of designing the scripting for yourself on it. The other thing this tool allowed us to do is it allowed us to test a lot more different machine types. Instead of sort of manually going through and picking out machine types, running through these multiple times in order to get significant results, now we can sort of use this open source tool to test many different ones out there. And so we've added the AWS types, we've added GCP types, and obviously we've added a whole large number of types from Microsoft Azure as well. And so the final point then is that we're going to be releasing this on November 12th is the plan. So it's a little under a month away. We don't have results to share today. I know people are probably a little disappointed by that, but we're still in the fact gathering portion of it right now. So we are very excited about it, and we'll be happy to share it with everybody in a little under a month. So with that, I will open the floor to any questions.
Quick question, the slide that you just showed didn't illustrate if you guys are looking at the Intel versus AMD processor types that have been starting to get rolled out on both AWS and GCP. And then second question was kind of, are you guys looking at all at time of day variants and region variants, seeing, is 8 o'clock in AWS East, different than what 2 a.m. looks like in that same region? Yeah, that's a great question. So the first question is that we are looking at the different processor types available. We basically have started to scour the different clouds for which is the latest available. And so several of them have multiple different processor types still available. Some only have the newest cutting edge version, but we were considering all the different processor types that are available on the public clouds. Your second question is actually pretty interesting, which is he asked, does performance change based on region or time of day? And our initial results last year found that there was some findings to that. There was some potential of noisy neighbor issues, or there's certainly availability issues that not all machine types are available in all regions. And the clouds want to have some predictability. There's this imaginary idea that you can just scale up and down, but there's real machine types that are behind that scaling up and down, right? And so they want to know if you're all of a sudden going to toss 100 or 1,000 machine types in a certain area, and they want to be able to predict it and plan for that. So it's a good question. We have not tackled it to date, but our sort of anecdotal testing does suggest that there's at least some performance difference. The approach we've tried to take is what is the best performance we can possibly get and demonstrate and provide. And so if we have run into something where some runs look really different than other runs based on time of day or those kinds of things, we tried to account for that in our testing to give the best possible foot forward for each of the clouds.
So I'll be as nice as I can because I am wearing the Google T-shirt, and I'm familiar with the original benchmark that was released in, you said November, December of 2018?
Yeah, that's right.
Yeah, it caused an interesting stir internally amongst our performance testing group inside of GCP. And there's some interesting findings that sort of came out of that, which is kind of interesting. However, one of the questions I want to ask you is just a generic question. Mm-hmm. How relevant do you think that the specific types of benchmarks that you're running are for generic workloads, specifically around f-sync and syncing after every transaction, which is the cause of a lot of performance degradation between the two clouds?
Yeah. So first off, thank you for your question. We appreciate you being in attendance. I think one of the things that we learned, again, last year is that we're in this space in which we're co-opetition is what I like to call it. We're competitors with Google and Amazon when it comes to their databases like Aurora and Spanner, but we need to be partners when it comes to the storage layer, right? We want our customers to be able to use GCP hardware and get good performance. We want our customers to be able to use AWS hardware and get good performance. And so I think a mistake we made last year was not reaching out to the teams in advance of, hey, here's the findings that we have. Like, are we missing something? Did we not think about this? And so that's something that we're going to correct this year, is that we're going to share our initial results ahead of time with the clouds, because we want them to, they might not necessarily like all the results that we find, but we want them to think that we were like fair and honest partners in the process. And so we want to show those things. And we've already talked about with Ping, one of the lessons we learned from Google about how to improve our findings there. And I think there's more to be had. We've actually had several meetings with some of the folks internally at Google. We've had several meetings with the AWS and with the Azure folks. And so I think it's a fair point that if we could rewind the clock, we probably would do things a little bit differently last year as compared to this year. Your second question was, how representative do you think this is? And that's a really tough question because one of the things I do as a product manager is I work with our SEs when they're dealing with different customers and they're saying, hey, tell me how many machine types I need to give to my customer. And I'm like, well, okay, tell me what their queries look like, tell me the concurrency that exists, tell me the frequency that you're accessing, tell me how much data there is, how much cold data, active data. There's all these factors that go into kind of determining the right answer here. And so, the thing is, we think this is representative in terms of the frequent syncing, but it doesn't mean it's representative for everybody or all the time. It's based on our understanding and our working with our customers. But that's part of the reason why we wanted to make these tools available and explain our analysis here is because for a certain customer, this may not be representative at all. And so we want them to still have the benefit of the learnings that we can provide that are at least relevant enough to them to then know what they need to test themselves. Cool. Well, one more question.
How do you or do you not deal with the possibility that, for example, in the one testing product, they discovered that they're effectively testing the CPU capacity to handle all these thrashing matrix calculations. So have you considered what happens when you run some of these performance tests separate from each other? For example, internal to my organization, we were doing some S3 testing. Mm-hmm. And, the way the tests were constructed, there were a whole bunch of things done. But then I pointed out to them, I'm like, what you should really do is just use up all the memory on the system and dump everything right out of memory. And they were asking why. I'm like, because you're not going to get more bandwidth and the speed out of that RAM down through that network card out to S3. And changes like that, as the system has to work together as a system, quickly demonstrated that there's major differences between various instance types, between various intermediaries, network connections that might be present. So when you use these benchmark tools, are you using them with a specific mind on how they interact with each other and how the system interacts with them?
Yeah, that's a really insightful and great question. So the question, that we think about this a lot because when we were starting to put this scripting together, was it fair to run everything back to back to back, for example? Did we need to run multiple runs of the same test over and over and then switch to the next test? And so we've thought a little bit about that. I don't know that we have a perfect answer yet for what that looks like. Part of the challenge that we're talking about here is that these tests in isolation are great because they tell you what CPU looks like when nothing else is going on here. But to your point, nothing is ever like that in the real world, right? And that's why we try to use TPCC as sort of our amalgamation of all these effects of things happening at the same time and what is the real implication of the performance difference? If we're seeing that a certain machine type has, less network ability, how does that actually translate to a workload like TPCC? And the answer is it's not as scientific as we'd like. It's really sticky. We don't have a correlation where if something goes down by a network a little bit that this impact happens on TPCC. Sometimes it does, sometimes it doesn't, and so it's a challenge for us to kind of think about those things. And ultimately, we're trying to shed a light on here. We're trying to challenge things in a certain way, make sure that we're as understanding as possible. But the only answer that you can actually be satisfied with this is to set up a test environment, run your exact workload on a machine type, use this type of analysis as a hypothesis to start with certain machine types, and then if you're not getting the performance you need, try it out on another machine type. There's certain, I think, we can keep you from having to boil the ocean of trying everything out there by doing some of this analysis, but I don't think that we'll ever be able to sort of conclusively tell you, CPU is this way, so it's going to have this effect on your workload, and this is what it looks like. Cool. Well, thank you, everybody, for your time. I'll stick around in case you have shy and want to ask questions afterwards, but we really appreciate the chance to talk with you, and thank you.